So we have a lot more things regarding the ideas of graphs and their first and second derivatives. So before we start, I think it's important to have an idea or a general idea of physics. That would help a lot in this scenario. So first we have the function. Now a function just relates two variables, so the function tells us nothing. Or just by looking at a function like x to the fourth plus 2x or something, that doesn't tell us much about the function itself. I probably couldn't be able to tell you the minimum or maximum about this function. So we have to look to the second and third derivatives, or the first and second derivatives of this. So the reason why I say it's important to know physics is because f of x is position, f prime of x is velocity, and f double prime of x is equal to acceleration. Now the reason why there are so much why physics and calculus are so connected is because Newton usually solved things in terms of physics, while Leibniz focused on the theoretical math aspect of it. So both different approaches to calculus. So let's go over the first idea, and this is in connection to my previous video, which I don't think I explained that well because I was sick. So the first idea is position, or not position, just a graph between two variables. Now we remember that Fermat's theorem states that if there's a max or min, f prime of x is equal to 0. But we also know one more thing, and I'm not too sure if there's a theorem named after this, but we know that wherever the function is equal to 0, those are the only places where sign changes can occur. So let's take a very simple function like f of x equals x plus 6. At x equals negative 6 is where the sign change occurs. Anywhere to the left of a negative 6, it's negative, and anywhere to the right of negative 6 is positive. So let's take a number to the right of negative 6, such as negative 3, and we get a positive number. And in the same way, if we take a number to the left of negative 6, like negative 9, we get negative 3, and then a negative number. So if we know that a maximum or minimum of f prime of x is equal to 0, then we can look to the sides of the function, of the derivatives function, to determine how the graph was changing. So in the general sense, let's take that same function x plus 6. Now, in x plus 6, there is no maximum or minimum because you can keep increasing it forever and ever. But let's add a little bit more nuance, and let's go x squared plus 6x. F prime would therefore be 2x plus 6, which means that x equals negative 3 is the only place in which a sign change is possible to occur. Now, I say possible because a sign change doesn't always occur at the place where x equals 0. It's just the only place that sign changes can occur, because we know through the intermediate value theorem a function must hit all points including 0 itself, between 2 points. So a function can't jump from negative to positive or positive to negative without hitting 0 first. So we know that it must hit 0 first, and therefore to the left and right side of it there is a negative rate of change, or a negative position if you take f prime of x as its root function. So we'll plug in a few numbers. Well, I already know the logic. Since 2x increases linearly, then we expect that as something gets more negative, the function also gets more negative. So here, in this case, the left side would be negative and the right side would be positive, logically. So let's take three cases in which the derivative to the left and the derivative to the right is possible in this scenario. Well, actually, let me just draw the curves to simplify things a little bit. So negative is, I think there's only two cases actually. So negative and, yeah, there's only three cases for sign changes, but we'll focus on the first one. Now, this looks like the derivative positive, 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 and it looks like a concave down function because it's getting less steep and less steep, and negative, 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 and negative. Now, the logic is clear. Once at f prime of c is equal to 0, which is basically any function that makes the derivative 0 or has a horizontal tangent, we see that it goes from positive to minus. And now that's very logical because it has to go from plus to a plus in order for the sign change to occur, or plus to a negative to hit f prime of c equals 0. That means the second derivative and the first derivative must differ in signage. And the reason being is because if they differ in signage, then that's the only place, or that's the only possible way for f prime of c to equal 0. In the same way, if you look at physics and we take the kinematic equations, we know that the second derivative of position, or I guess that's the first derivative of position, the first derivative of position is equal to the velocity the initial velocity plus at. If the initial position, oh sorry, that's would be VO. If the initial position is positive and this is also positive, then there's no way it hits 0 because it just is greater than 0 at all points. Therefore, we know that the second derivative and the first derivative must differ in signage, which is where the second derivative test comes into play. So before we start, it's important to note that the first derivative has a plus or minus, which indicates maximum. And to memorize this, well, for me, I don't memorize things. I just figure it out in my head, because what's the point of memorizing things if you don't understand how they work? So logically, it has to be positive to get to that high point, and then minus to go down. And as we know, definition of a maximum or minimum is that it's higher for x near C or x for all C if you say absolute. So essentially, if it's greater than x minus c, that means all the points must be approaching from the left and the right the same idea. So kind of like a limit idea, they must be approaching the same point. And if you flip the right side 180 degrees, it would be positive. So in the same way, this is logical. Or you can think of it just as that the function has to be positive to reach that really high point. You have to think of it like a mountain. You have to be going upwards to hit the top point and downwards to hit the minus point. If it's neutral, which means that both sides of f of c prime equals 0 is 0 or horizontal, then that usually means just a linear line throughout that interval, meaning that f prime of x can be constant, but this is simply just no max or min. Now we get to the second derivative test in a little bit. And then the last one will be minus positive, which if you guessed it would be minimum. Now again, these don't tell you anything about maximum or absolute or relative maximas or minimas. And to do so, I think it would take some logic and figuring out. There's not a foolproof way to do it for each function, I'm figuring. But like for x squared, you can assume that there is no number smaller than the vertex. So logical stuff like that. So that's the first derivative test. We get to the second derivative test. Now remember what I was talking about. And we'll use a quadratic function simply to model two derivatives where the third derivative is constant, or the second derivative is constant. So we have f of x equals x squared, and f prime would then equal 2x, and f double prime would equal 2. So let's draw the graph, and the graph, as everyone knows, is a parabola. And let's look at the slope. So we've mentioned before the first derivative test, we know that the slope is negative here and positive here. Why do we know that? Now, there's something called intervals of increase and decrease. Now, the intervals of increase are, as you know, or as it sounds like, as it's obvious, where the function is increasing. And the intervals of decrease is where the function is decreasing. So this entire left side would be intervals of decrease. And we would know that through the sign changes, as we've mentioned before. If f prime is negative, then it's in intervals of decrease, or it's decreasing, and if f prime is positive, it's increasing, because f prime measures how the function is changing. But we notice here that the derivative goes from, or the f prime goes from negative to positive. But how does it do so? Well, we know that f double prime is basically how f prime is changing. So that means this has to be positive at some points to turn this negative into a positive. So in the same way in calculus, or in physics, I mean, if we have VO plus AT, which is the first kinematic equation, I believe. I know physics, I just forgot which number it was. Then we know that A has to be differing in magnitude. So it comes to the second derivative test, and this is logical. Well, we can use Fermat's last theorem, which states that if f prime of c equals 0, comma, and, so we have two conditions here, two Boolean conditions, and f prime of x, or f prime of c, is greater than 0, which basically means that the slope is changing positively at that point, then it's a minimum. And that's logical because, let's take this here, the slope has to be changing to a positive slope, or the slope must be changing positively from a negative to a positive slope, meaning that it must hit 0 right here. Where the slope or horizontal tangent is 0. So in the same way, f double prime of c being greater than 0 indicates that f prime of c, or f prime of c is less than 0, or not f prime of c, that f prime of x is less than 0 when x is near c. And that's where the logic occurs. That's f prime of c must differ from f of x, where x is near c, because or where x is left of c, I guess would be the logical conclusion here, because they have different signage, much like physics, where f prime of x has to be, or I guess it'll be f prime of x, where f prime of x has to be transformed by a number opposite in signage. Because a positive plus a positive will never yield 0. So we know that for it to go from negative to positive, which as we know is a local minima, then f double prime c being positive is greater than 0, and we also label f prime of c as a concave up. So the logic is as follows, and I'll just write it down. F prime of c is, let me just put if f prime of c is equal to 0, and so we'll have two conditions here, and f prime of c is less than 0, comma, f of x, f of c is a local min, actually local max here, it would be f prime of c is greater than 0, local min. So again, just opposite in signage, f double prime of c greater than 0 means that the right side is positive and the left side is negative. Now, there is something I realized, and I guess this is an objection to what my textbook says, because I guess this goes into real analysis a little bit, and the analysis of limits and delta epsilon proofs. But I had an idea, and I said, okay, well, we're looking at this instantaneously, and we're saying we're taking 2 points. We're just taking 2 points as f prime of c is equal to 0 and f double prime of c. That's all we're analyzing. But I realized something. Is it possible for a function where the f prime of c is positive and f prime of c is equal to 0, where to the left it never switches signage, so it just goes from positive to 0 to positive? And it got me thinking, well, that is the case if we take the first derivative test and we look at f prime of c. It is very possible that a function hits f prime of c is equal to 0, and then just goes positive after. And a function, I'm trying to think of one. I guess x cubed would be a very good example. Here, nothing is happening. It's going from positive to positive, and there is no absolute maxima or relative maxima here. So the logic is as sounds. The logic is that f double prime of c can't change directions, because for it to go from positive to 0, that would indicate that f double prime of x had to be negative where x is near c. Where x is near c. And why is this the case? Because there had to be an f double prime of x that changed the positive slope to a negative slope. And because f double prime of x is negative, then it had to go to 0 and go to positive, such that at that instantaneous point, where in this case x equals 0, f double prime of c had to be greater than 0. So here it had to start from negative to make this hit 0, then go to 0 and go to positive, so that it's positive in this case. And that breaks the logic here, because in this logic barrier there is no maximum or minimum here. So it's very possible that in the second derivative test there actually is no maximum or minimum, regardless of if f double prime of c is greater than 0. So it got me thinking, logically, are we able to make a more precise definition? And I'm sure mathematicians have already done this, it's just not in my book, that there has to be an interval where the sign change doesn't occur. Now, what do I mean? So let's just take x cubed, for example, and let's differentiate it once and differentiate it again. 3x squared, 6x. So we know that at 6x there can be a sign change. Actually, it's probably better not to give an example because I can't think of any right now. So let's start from the first function, which doesn't really matter. So we'll skip the first function and just go to the first derivative. If it starts on a number line, and let's just say that this is c, which equals 0. So this is f prime inputs, so f prime of c, f of whatever, f of a and f of b, or f prime of a and f prime of b, and this is negative and this is positive. That indicates a local minimum. But what happens if this is positive, as we were just talking about before? Well, this is also very possible, and the f double prime would probably look something like this, where f prime of c, and we mentioned that this is positive, and we mentioned that to the right of it, well, we wouldn't know because we were looking at it instantaneously, and we'll say B and A. There had to be some interval where this was negative to turn this to 0. So in this case, you can keep going smaller and smaller, and putting this interval here and this interval here, such that if a sign change does occur, then that means there is no maximum or minimum. So there has to be a very, very tiny sliver, which can be 0.000000001. And I think to do this in epsilon proofs, it would probably look something like this. If f prime of x minus, or actually I don't think there's a conditional statement here, minus f prime of c is greater than 0, comma, when x approaches c, or when c approaches x. Well, I guess x would be the input here, comma, there has to exist a f of c that fulfills max or min. And that's as close as we can take x or c. Actually, probably there has to exist, well, because that just goes back to Fermat's theorem, there has to exist a delta greater than 0 such that x minus c is greater than 0, comma, that f prime, or f double prime of x minus f prime of c is greater than delta as well. So there has to just be a tiny, tiny interval in which there's no sign change between the f double prime of x to ensure that that the function is smooth and that the function has a local maxima or local minima at that point. Because if it changes signage, then it is very possible for it to just be 0, or to be positive before and positive after, because there was a negative point that just made it hit 0. So that's the logic as follows. I'm going to try to summarize it one more time. If f prime of x, there's an interval here where this is c, and this would be to infinity and negative infinity. And if it's positive all throughout, it can be positive right until this instantaneous point, and then turn positive again. And then for f prime of x, we have c. And because for f prime of x, we can theoretically check intervals using, again, the method I used, which you'll have to make a number line for. There has to be, like, let's say that there's a difference in sign and it becomes positive right at this point. So we have a very small interval here. If there is no jump between f prime of c, or f double prime of c, and whatever makes this negative, if not even one number exists between those points, then that would basically say that it's very, very possible that, sorry, let me think, I'm getting a little ahead of myself. It's very, very possible that there exists that the function was already positive before the second derivative kicked in. And by doing so, we know that there is no sign change there. So the logic only applies because the second derivative implies that f prime of x is different. But we know that before there could have been just a very small sliver of negative, or even a very large sliver of negative, that could have made f prime of x from greater than 0 to f prime of c is equal to 0. So the f double prime of x being positive doesn't necessarily tell us that f prime of x was negative before, which is necessary for the first derivative test. So that's the logic there. And yeah, I think that was pretty intuitive there, pretty intuitive thinking. So I'm hoping to get some answers, because I don't really know too much about delta and epsilon proofs. I haven't taken real analysis yet, so